Hi everyone, today I'm going to go over the lab activity worksheet. This is going to be working with our assembly code and learning how to use the instructions to build the stack and then also find what the code this function is supposed to represent in assembly. So first questions that we're going to answer are how many stack bytes are used, and then we want to ask what value is actually printed to that standard output. So I have our sheet prepared in a different format just so it's easier for us to do our work and see what's happening. All the functions are the same, I just reformatted everything. So to start, we should know that this is our main function, and within our main function we're calling our other function 5149, and it starts right here, and we're just going to call this function A. On the right we have our stack. Notice how there's a difference of 8 bytes between these addresses, -8 minus 0x8, and then we have our base and our stack pointer right here, and we know that our base pointer is going to be at E4E0 and our stack pointer will be at E4D0. And now our RIP, or our RIP, will tell us what instruction to start at. So it says 518D, so that means we're going to start right here. Now we can get started with actually going through that assembly and seeing what's happening. So our first instruction is to move 0x0 into -0xc RBP. So to calculate this address, we have to find -0xc RBP is equal to 0x RBP E4E0 minus 0xc. Remember, we have to pad the rest with 0. So we have 2 bytes here, so 0 minus c is not possible. So we're going to borrow from E, we'll get D, and then this becomes 16 minus C, which is 16 minus 12, is 4. So E4, D4. And looking at our instruction, we're moving L. So we're going to move 4 bytes starting at this address. So over here, we're going to have 4 bytes of our value 0x0. If we look at our stack, we'll see we don't have a E4, D4, but we know that D0 corresponds to this last byte over here. This is D1, D2, D3, and D4. Now starting at this address, we're going to fill in the remaining 4 bytes, or the remaining 3 bytes with zeros, and this is what it'll look like. And then these last 4 bytes are going to be unknown, so we'll just put an asterisk for each unknown byte here. Next instruction, moving 0x3 into -0x8 RBP. Let's calculate that address. 16 minus 8 is 8, so we get that the address at -0x8 RBP is E4D8, and we're going to be moving 0x3 and starting at that address. And remember, we're moving 4 bytes, so we have to pad to 0, so it's a total of 4 bytes. 1, 2, 3, 4. So let's look at our stack, look for E4D8. So starting at D8, we're going to put in our 0x3, and we need those 4 bytes, and we don't know what these 4 bytes are, so we'll just put in those asterisks again. Now we're taking the values that we moved into these memory addresses, and now we're going to put them into our the last 4 bytes of these 2 registers. So EDX, EAX are the last 4 bytes of RDX and RAX respectively. So let's go keep track of these registers. And we have EAX. Okay, and now we're going to move whatever values at this address into EDX. So that value would be 0x03. So EDX is the last 4 bytes. So it's now going to look like this. And our EAX is going to have this value placed inside it. So that's what our EAX and EDX registers look like now. Now we're going to go down and we're going to move EDX into ESI. ESI is a register we haven't accessed yet. Again, it's 4 bytes, and we're going to take EDX, whatever's in EDX, and put it in there, so it's going to be 0x03. And now we're going to move EAX into EDI, so now EDI will have the value of 0x0. Now, we're going to move to our call function, and this means that we have to, 1, allocate 8 bytes of space on the stack. So this means that we have to, so now we have to allocate 8 bytes on the stack for our call function. So we're going to subtract 8 from RSP, 8 bytes from RSP, so now RSP moves up towards the lower address on the stack, and now it will be at E4C8, and we're going to move our return address into whatever this value, this space is. So our return address is always going to be the address of the instruction right after our call. So that will be 0x51AA. That's going to be placed right here. This is important, so then when we're finished with the function that we're calling, we can always return back to the next instruction. And then we're going to jump to the label. Our label is 5149. 5149 is right here, so that's the beginning of our function A. Okay, now that we're here, our first step is to push RBP. You should remember that push RBP means we're allocating more space on the stack. So first we have to subtract 8 from RSP, and RSP is going to go up again towards the lower memory address, and now it will be at 0xe4c0, and then we have to place the value of RBP, E4E0, into this space, which means that the value that this memory address points to, E4C0, will be E0xe4E0. And then we're going to move RSP into RBP. So now RBP, which was at E4E0, will now have the same memory address as RSP inside it. So now RBP will be pointed at that same address. Now we have to actually allocate 16 more bytes of space on the stack, since we're subtracting 0x10 from RSP, which is 16 bytes. So now RSP is actually going to go up 2 spaces. RBP will remain the same. Let's find out what the address is. You know, the next address below this, 8 bytes below this, will be B8, and then RSP will be at E4B0. Now, look, we're moving EDI and ESI into some new variables. So EDI and ESI, we had set the values of right over here. I'm going to highlight these registers so we can keep track of them later. I'll place it right here. Okay. Now we're moving EDI into -0x4 RBP. Right now, -0x4 RBP is going to be, where's RBP? RBP is at 0xe4c0. 0xe4c0 minus 0x4, 0, this will be C, this will be 12, which is C, and then B, and then E for 0x. And this, at this point, EDI is, the value of EDI is being placed in there, and EDI right now is 0x0, so E4BC will have 0x0. Let's go look at our stack. When we want to look for BC, we know that B8 is at this first byte, then we have B9, we have BA, we have BB, and then we have BC. So starting at this address, we're going to fill it in with 4 bytes of, remember it's EDI, which is 4 bytes of 0x0. So this will be 0, 0, 0, 0, 0, 0, 0, 0, 0, and that is 4 bytes. Again, we don't know the value of these remaining 4 bytes at the end, so we'll just do an asterisk. Our next step will be very similar to that. We have to calculate 0x8 RBP, which is 0x4C0. And ESI has the value of 0x3. This means that we're going to fill in, starting at B8, which is right here, these last 4 bytes, we're going to fill it in with 4 bytes. And those 4 bytes will be 00000003 from moving ESI, which is 0x3, into the value of this memory address. Okay, our next step is we're going to move 0x4 RBP into EAX. 0x4 RBP, the value at that memory address is currently 0x0, so we're going to place that into EAX. So now EAX, which is 0x0, is going to be 0x0. So this will be after this. Okay, and now we're at a compare statement. So we're doing compare, and then we'll jump if these two values are not equal. If we jump, we're going to jump to this label, which is 5168. 5168 is all the way, 5168 is right here. So we're going to compare minus 0x8 RBP, which is currently 0x3, and we're comparing EAX. And EAX is currently 0x0. Those two values are not the same, so we're going to jump. So now that we jump, we're going to this instruction, and now we're going to move minus 0x4 RBP into EAX, which means it's going to be 0x0 again. We're going to load effective address 0x1 RAX, and then move that into EDX. Notice that this is only 4 bytes. Remember, EDX is the last 4 bytes of RDX, so we're actually only dealing with the last 4 bytes of RAX in this case. So RAX, which was 0x0, we're going to add the offset, which is 0x1. So 0x0 plus 0x1 becomes 0x1. And instead of going to that address and then looking at the value that that address points to, load effective address is just going to take this address we calculated here and then put it into EDX. So now EDX will have 0x1 plus 0x0, which is 0x1. So EDX will now become, EDX will become 0x1. Now we have to move minus 0x8 RBP into EAX. So minus 0x8 is 0x3. So now we're going to put 0x3 into EAX, and then we're going to move EAX into ESI. So ESI now becomes 0x3. EDX is moved into EDI, so EDI becomes 0x1. And now we're going to call this address. So the call instruction involves moving the RSP pointer up towards the lower memory address, so allocating 8 bytes of space. This new address will be E4A8, and then we're going to move the return address into the space. So we're going to move 517A into this part right here so we can return to it later. And now we're going to jump to this address, 5149. And then we get to go through our function again. So again, we're going to push RBP. This involves moving RSP. We're moving RSP up. We're putting the address in RBP inside that dereferenced memory address. Then in our next step, we're moving that address of RSP into RBP. RBP goes up. Then we have to allocate 16 more bytes. That's what 0x10 is equivalent to, 16 bytes. RSP goes up by 16 bytes. So this is what our stack and base pointers are at right now. Then we'll move EDI and ESI into our new local variables, 0x4 and 0x8 RBP. So now we have to recalculate them because our base pointer has changed. So now our new RBP is at E4A0. This becomes C9E40X, and we're going to move EDI into this dereferenced address, so E49C. EDI is going to be 0x1, and And then for the minus 0x8, so that's our new address. And inside this dereferenced address, we're going to place ESI, and that becomes 0x3. Now we're going to do the same process of moving 0x4 into EAX, so then we can compare it with our 0x8, comes 0x1. 0x1 is not the same as 0x3, so we're going to jump, and we're going to jump to 5168. Now that we're at 5168, we're moving 0x1 into EAX again, and go down. We're adding 1 to our EAX value and placing that in EDX, so 0x1 plus 0x1 becomes 0x2. Then we go down, we're moving minus 0x8 RBP into EAX, so that's moving 0x3 into EAX. Move EAX into ESI. Then move EDX into EDI. Then we're going to call. Again, call requires our RSP to create space for another 8 bytes. 8, 8. We're going to move our return address into this space, which is 517A. And then we jump to that address again. So 5149. We've restarted our function, and we're back to the start. Looking back on our registers, we can tell that there are some patterns. So our ESI stays constant. So we can look at our registers in our local variables by now and kind of notice a pattern. We notice that our ESI stays pretty consistent. It's the same 0x3 value, and that value is the one that keeps resetting our new local variable every single time we're going through this function, which means that this variable must have to stay constant in this function, so we're not changing it, whereas EDI is actually incrementing by 1 so far, and we see that our EDI over here is resetting our minus 0x4 RBP value. So that value is the one that's changing in our recursive function. And then it looks like our EAX is being used just as a register to be able to set other values and then help us manipulate some of our variables. All right, let's go through this problem again. So we're pushing RBP, RSP goes up, RBP's address goes in here. Then when we have to move our RBP is at this point, and then our RSP has to go up by 16 bytes. And once we get to this point, again, we have to recalculate our new 0x4 and 0x8 variables. So minus 0x4. Our new RBP is at E4780. And our new minus 8 RBP is right here. And then at 7C, we see that we have EDI being moved into there, so this becomes 0x2. And then our minus 8 RBP stays the same. It's always at 0x3. One thing I forgot to mention before is we do have to go into our stack and then update these values. So let's go look at 0xe498. That should be 0x3. So at 98, starting at that last byte, it's going to be 03, and then we have to pad, so it's 4 bytes. 1, 2, 3, 4. And then, starting at 0xe49c, we're placing 0x1. So this would be 1, and then 2, 3, 4 bytes. So that's what's happening over there, and then we're going to do that again starting at 0xe47. 16 minus 8. 8 is 8, and then 7, 8. Okay, and this will have 0x3. So 0xe4783, and then we have 2. Okay, now we're at a point where we're moving minus 4 RBP into EAX. So now EAX will have 0x2, and we're comparing 0x2 and 0x3 over here. They're not equal, so we're going to jump, and that brings us all the way down to here. Moving 0x4 RBP into EAX again, adding 1 to that value so we can place it into EDX. So 0x1 plus 0x2 is 0x3. Moving minus 8 RBP into EAX. So EAX will have 0x3 again. And then we have to move EAX into ESI, again keeping that constant value, and then move EDX into EDI. So then now our EDI gets updated through our EDX being updated. So then later when we go through this function again, our EDI, our updated EDI, is going to update our 0x4 value. Okay, after that we get down to this point. So we're going to call, we have to make 8 more bytes. Oops, this is 0xe468, and then we have our return address that has to go in here, 517A, and then we jump and we're back at the beginning. So we're pushing RBP goes up, xe460, putting the address inside RBP in here, E480, and then later we have to move RSP into RBP, so then our RBP will go right here, then we're subtracting minus 0x10 from RSP. Now we get to update our local variables again. We have to find that new minus 0x4 RBP and 0x4 RBP, minus 0x8 RBP. Okay, so we're going to do that by doing 0x4 RBP equals 0xe4. Our new RBP is at 60 minus 0x4 5c e4 0x 0x. Okay, so then we're moving EDI into minus 4. So EDI is 0x3 right now. That's the new value we calculated from the last time. And then E458 will remain as 0x3. Now we get to go into the addresses here and then update the values. So starting at 58, it will be 3. And then we're placing 3 in there again, starting at 5C. Okay, now we have to move 0x4 RBP into EAX. And we'll compare. Is 0x3 equal to 0x3? Yes, it is. So now, instead of jumping, we're going to go down. Oh, instead of jumping, we're going to go over here, and we're going to move 0x4 RBP into EAX again. So that becomes 0x3. And then we'll jump to 517F. Once we jump to 517F, we're going down here, and then we're going to leave our function. The leave has a couple of equivalent assembly instructions. Leave means we're going to move RBP to RSP. Then we're moving the dereferenced value of RSP into RBP. Then we're going to add 8 to our RSP. And then for ret, we're going to add 8 to RSP and then move minus 8 RSP and place it into our IP, which is like the next instruction. Okay, so let's do that. Let's do our first leave instruction. So we're going to move RBP to RSP, which means that since RBP is at 0xe460, RSP will also be there. RSP and RBP are going to be at 0xe460. Then we have to move the dereferenced value at this address and then place it into RBP. So that's E480 right here. So now RBP is going to be at E480, which is right down here. And then we have to add 8 to RSP, which means we're moving down. So RSP will be going down 8 bytes, or we're adding 8 bytes. And then we're going to do our return instruction. So return is going to add 8 to RSP again. But then after that, it's going to find the address minus 8 of the RSP and then dereference that and then place that into our RIP register. So if we go up by 8 and we look in here, this is going to be the next instruction that we have to perform. So that'll be 517A, which means that we have to go over here and we have to move minus 0x4 RBP into EDX. So at this point, we have to move minus 0x4 RBP into EDX. So minus 4 RBP is going to be starting at this address right here because we're at E480 minus 0x4 is going to get us to this address. So EDX will be equal to 0x2. And then after that, we have to add EAX and EDX and place that into EAX. So EAX is 0x3 right now. So 0x3 plus 0x2 is 0x5. Okay? After that, we perform that leave instruction again, which means that RSP is going down to where RBP is. Then we're going to this address in here, and RBP is going to go there. So E4A0 is down here. RBP is being updated. Then RSP, we're adding 8, so it goes down towards the higher address. And then in our ret instruction, we're adding 8 to RSP again. Then we have to move minus 8 RSP and dereference that and move this into our RIP. So again, we're going to 517A. So we have to go to 517A. We have to move minus 0x4 RBP and place it into EDX. So RBP is right here, and minus 4 RBP would be right here. So EDX is now going to be 0x1. We have to add that to our EAX. EAX is 0x5. 0x5 plus 0x1 is 0x6. Then we're going to perform leave again. RSP goes down. RBP gets updated to this address, E4C0. RPP goes down here. RSP, we add 8. Then when we get to our ret instruction, we add 8 again. We go 8 bytes down. We find this address, and then we go perform that one last time. So now EDX, right now we're right here. We're going to find minus 4 RBP, which is 0. And we're going to place it into EDX. And then we're going to add 0x0 to EAX, which is 0x6. Okay. And then we're going to go perform this leave again. We're moving RBP to RSP. RSP goes down. Then RBP goes to this address, E4E0. RSP goes down by 8. And then because of the return instruction, it's going down by 8 again. By going down, I mean it's moving toward the higher memory address. So it's going to go to 8. And then we're going to go up here, and we're going to put this address into our RIP, which means this is the next address that we're going to perform. So 51AA is right here. So we're going back to our main function. Remember, when we called this, we had put this return address into the stack intentionally so we could always return to it. So that's what's happening right now. So we're going to this instruction, and we have left our recursive function. And these are the updated values of our EDX and EAX. Now that we're in our main function, we're moving EAX into minus 0x4 RBP. So EAX, which is 0x6. So minus 4 RBP. Now these values before that we thought were unknown, we're going to move our EAX into there. So we're moving 4 bytes. So that will be 0.6, and then fill it in with zeros. Now we go down here, and we're moving that into EAX. So EAX is just going to be 0x6 again. Then move EAX into ESI. So then our ESI, we're moving EAX into ESI, so now ESI will have 0x6. Then we're going to load effective address. We're going to add this offset to our RIP address and then place that into RAX. So our RIP would currently hold the value of the next instruction. It would be at 51B9. So E4B plus 51B9, let's calculate that. 9 plus B is 9 plus 11 equals 20. 20 is equal to 1 times 16 plus 4. This 4 goes down here, and this 1 is carried up here. 1 plus B is 13, or 1 plus B is 12. 12 plus 4 is 16. So 1 times 16 plus 0 equals 16. So this 0 will be placed down here, and then this 1 is going to be carried up here. 1 plus 1 is 2, 2 plus e is 2 plus 14, which is 16, so this is just 1 times 16 plus 0 again, which equals 16, so then that 0 goes down here, and then this 1's carried up here, and then 1 plus 5 is 6, so we get our final value is 6004, and this will be placed into RAX. RAX is the full 8 bytes, so RAX will look like this. Okay, this is going to be 8 bytes total. So now we're moving on to the next instruction where we're moving RAX into RDI. So now RDI, the full 8 bytes will look like this. This will be the address of the string format, or the format string, for our print statement later. And then after this, we're going to move 0x0 into EAX, the last 4 bytes of RAX. So now this 6004 just becomes 0. Then we're going to call 0x5050, which is just print RSI. In the original lab activity worksheet, it said print RDI, but it should actually say print RSI. So what's going to happen is we're going to look inside our RSI, and our RSI is equivalent to 0x6. So the actual printed output will be 0x6, or 6 in decimal. So that's our output. We can see later on we're going to move 0 into EAX, and we're going to leave, so we're going to return that 0, which means the main function is done. And then the second question we wanted to answer was the stack size. And we can find this by actually going into our stack over here and counting each row and then multiplying that by 8 to find out how many bytes we used. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we have 20 total rows. We're going to multiply that by 8 bytes, and that will get us 160 bytes. So that's going to be our stack size. So that was a general walkthrough of how to work through a recursive function, and then learning how to use the call instruction, leave, and ret, and then also at the end trying to find that printed statement and then the stack size. So good luck, and I hope this video was helpful.